If we have a number m that divides the difference of two other numbers, it can be more convenient to rewrite this as a modular equivalence. So this is the same as x is equivalent to y in mod m. So we'll do that here for this problem. We have m is one of three numbers, 2, 3, or 5. And rewriting this problem statement, we have a sub n plus m is equivalent to a sub n in mod m. Let's start with m equals 2. And we'll start with n equals 1. Then we have a sub 1 is equivalent to a with a subscript, 2 more than 1. So 3, 5, and so on to our last odd subscript, 29. If we start with n equals 2, we can add 2 more to this, and then we get all the even subscripts up to a sub 30. These are all equivalent in mod 2. This means this first group of 15 terms, they're going to be either all odd or all even. If they're all odd, then the second group of 15 terms is going to be even, or vice versa. For now, let's just say that there are two ways to assign these two mod 2 residuals to these two groups of 15 terms. Let's take a look at m equals 3. If we start with our first term, a sub 1, it's going to be equivalent to a with a subscript that's 3 more than 1, or a4, and so on. This will be equivalent to a7. Our last term that fits this pattern is a sub 28. If we start with a2, this is going to be equivalent to a5, and so on, up to a sub 29. And then if we start with a sub 3, we get all the multiples of 3 here, up to a sub 30. We have three groups of terms with 10 terms each. These are all equivalent in mod 3. So let's say that there are 3 factorial, or 6 ways, to assign one of the mod 3 residuals, either 0, 1, or 2 in mod 3, to each group of 10 terms. Finally, let's look at m equals 5. And we'll start with a sub 1. We'll add 5 to that subscript, so this will be equivalent to a sub 6, and so on, to our last term, a sub 26. a2 will be equivalent to a7, etc., up to a27. We'll continue this to our last group, starting with a sub 5, which will be equivalent to all these terms up to a sub 30. This is in mod 5. We have 5 groups here consisting of 6 terms each, and we have 5 mod 5 residuals, so there are 5 factorial, or 120 ways, to assign all of our mod 5 residuals to these 5 groups. We can do these assignments independently of each other, so the total number of ways to assign these 3 groups of residuals is going to be the product of these 3 numbers, 2 times 6 times 120, or 1440. To see why this is true, let's say we want to assign a number to a1 in one of these particular arrangements. So let's say that everything in this top group here is going to be equivalent to 1 in mod 2, including a sub 1. So we'll say that a sub 1 is 1 in mod 2. For m equals 3, we'll take a look at a1 again, and let's just say that everything in this first group is going to be 2 in mod 3. And down here in mod 5, let's just say that everything in this first row, including a1, is going to be 4 in mod 5. We have that the GCD of 2, 3, and 5 is 1, so we can use the Chinese remainder theorem, which gives a solution for a sub 1. It turns out that's 29 in mod 30. This is going to be true for every AI in our sequence. We will have one solution for each one of our 1,440 ways to arrange these residuals among our groups of terms. So 1,440 is also the number of permutations of ways we can assign the numbers 1 through 30 to all of these terms, a sub 1 through a sub 30. And the remainder, when dividing by 1,000, is 440, and that's our answer. If you'd like me to solve any other math contest problems, please leave them in the comments.